Okay, so the next talk is by Schlosser, and it's elliptic extension of the multinomial theorem.
Thank you very much. It's a pleasure to be here. I would like to thank the organizers for inviting me, and also there's been a great workshop so far. Pardon? Is the microphone on?
No.
Do I need to switch it on? There's a button, I'm sorry. Where is it? Okay, can you hear me now? Okay.
Yeah.
So I would like to thank the organizers, and it's a great workshop and wonderful talks. Okay, so here's the outline of my talk. To give you a feeling what I want to extend, I want to review the basic setting, the trigonometric case, the non-commutative Q binomial and Q multinomial theorems. So these are well known, but that you see what I'm looking for. I will extend those to the elliptic setting, and the motivation is to prove some identities in the theory of elliptic hypergeometric series. So the Q binomial theorem, the elliptic version, works to prove the Frankel-Derive sum, and the multinomial version will be which helps to prove the multivariate extension of that. An AN extension, or AR extension, which we will see in the end. So the method will be combinatorial in a sense, or algebraic and combinatorial. So the combinatorial framework is using lattice paths. The algebraic framework is using non-commutative variables, or quantum algebra. So I will use elliptic weights. They will be used to define elliptic binomial and multinomial coefficients. I will explain what elliptic commuting variables are, so they will be extensions of Q commuting variables. And then you will see what the elliptic multinomial coefficients are. These are closed form products consisting of theta functions, and the elliptic multinomial theorem you will see with application, as I mentioned. Okay, so here's some notation. I think I can probably skip this. This is the Q binomial coefficient. It should be well known. It's a product of linear factors, but it's known also that this quotient. This is actually a polynomial in Q of degree k times n minus k, and there's some explicit definition for these Q-shifted factorials that will be extended to the elliptic case a little bit later. For the Q case, here are these Q commuting variables. We work in a quadratic algebra. We want to normalize monomials so we have two variables x and y. We want to put the y's to the most right, then the x's, and then the coefficients subject to this quasi-commuting relation. And so if y appears before x, we want to reorder it, to normalize it, then it generates q. Later there will be an elliptic weight instead. Right now the Q commutes with everything, but later the weights which we have in the elliptic case, they will not commute with x and not with y. Of course, this can be regarded as a Q deformation of the commutative algebra in x and y. We refer to these variables as Q commuting variables. Later we will have elliptic commuting variables. Here's this famous theorem by Harold Potter, not Harry Potter, and Schultz Berger, which just more or less says that in this algebra, if you expand x plus y to the n and normalize it, the coefficients are these Q binomial coefficients. In particular, they factorize completely. It's easy to prove by using using the definition of the Q binomial coefficients, and to see that it actually can be also defined by this, uniquely by this recursion. So you have, this is a Q-Pascal triangle relation. I think I don't need to explain much. Maybe just this particular factor Q to the n plus 1 minus k, that's like a weight, can be regarded as a weight of, in the lattice path picture of a horizontal step of height n plus 1 minus k. In the elliptic case, there will be a theta function instead of product of theta functions there. But else it will be quite similar. Okay. Here is the extension from two variables to r variables. So we have n being an integer, non-negative, k1 to kr being additional integers, satisfying this restriction that the sum is n. This is the well-known Q binomial coefficient, products of Q-shifted factorials. It's again a polynomial in Q actually, with non-negative integer coefficients, which can be easily seen by checking that this Q binomial coefficient, Q multinomial coefficient satisfies this recursion. So everything is Q positive. Again, it's a Q Pascal, not triangular relation, not triangle, but tetrahedron or multi-tetrahedron. Okay, so this recursion, and this could be checked by using this definition and using partial fraction decomposition. That is one way, but you will see that in the elliptic case. Okay, now we have our Q deformation of the commutative variables, commutative algebra and R variables. This is also well known, so if you have two, as a quadratic relation here again, you want to normalize these variables ultimately so that the xr appears to the most right and the xr minus 1 and so on. And so if it's out of order, xj, xi, you want to renormalize it, normalize it. It generates q for any pair I less than j. In the elliptic setting, we will have different weights instead of q. And also, we will have additional relations. So these are now Q commuting variables. And here's the non-commutative Q multinomial theorem, which again says that after renormalization of x1 up to xr, the sum of these to the power of n, the coefficients are nice, and these Q multinomial coefficients. I haven't been able to trace the first appearance of this formula, so I call this a folklore result. But so if anyone has an idea where, so Schüssen-Bachet is not in there, it definitely appears at many places, but I don't know. So people have not made a big deal out of it. They've said, okay, fine, similarly this can be proved. Yeah. Okay, so now I want to extend this to the elliptic setting. I'm working now with theta functions, now with these modified Jacobi theta functions, which means more or less that I just take I use also this multiplicative notation for theta functions. So theta of x, the x is more or less, theta of x is more or less extension of 1 minus x. So that you should think of. So if you're not so familiar with this, but you are definitely because it's an elliptic workshop, you should just think of simple products of linear factors, but now they are extended periodically, let's say. We have infinite products. So this is the Jacobi triple product identity. Of course, you can write this as a sum, but this is not the point. What you might not be so familiar with, because I'm working with explicit expressions, I'm using theta-shifted factorials. So AQP sub k is now this product of k factors, and where each factor is an analog of these linear factors, so this extends the Q case. Okay. Now I'm using compact notations for products of theta. Yes, and the norm P is I'm suppressing, because the norm P is always the same. I'm not changing that. So I'm assuming P to be the norm. P should be less than 1 in absolute value. Then I also write a compact notation for these QP-shifted factorials. Okay, so of course one can always generalize, but something has to carry over to the more general setting so that it makes sense. And of course we have some simple identities satisfied by these theta functions. This is this inversion formula, a rule for replacing x 1 over x, and quasi-periodicity to multiply x by p. And more importantly, and more non-trivially, we have this addition formula. A product of 4 theta functions minus another product of 4 in a particular way equals again a product of 4 theta functions with 4 variables, with some certain nice conditions. You can put this right-hand side as a denominator here, and then you see that each term is elliptic. And the right-hand side would be one constant, which is also elliptic. But Okay, I haven't defined elliptic function yet, but anyway, probably you're familiar with it. So this identity is crucially used in the theory of elliptic hypergeometric series. So in inductive proofs, functional equations, so all these, many of these proofs, the machinery uses this additional formula. In the AR setting, so if we work with R-dimensional series, or instances of the type A elliptic partial fraction decomposition due to the Ashtas, this is used instead. And actually the R equals 3 case, so you have just 3 terms on the left-hand side. After rewriting it, clearing denominators, you get this addition formula up there. But that's also due to Ashtas. And it appears in Whittaker and Watson form as well. Yeah, and there is this you will also see very often. This is an elliptic condition, elliptic balancing condition called, okay, maybe just balancing condition, but it's so that applying this quasi-periodicity rule, the contributions in the numerator and the denominator, they should cancel. So that's more or less what this tells them, but with each term similarly. Okay, so what is an elliptic function? I don't mean a special elliptic function like elliptic integrals of first and second kind, so that is what I would rather call special elliptic function. I mean, elliptic function in general is just a meromorphic function, which is also doubly periodic in its variable. And then it, without loss of generality, so any elliptic function can be written as this quotient of theta functions, where S is the order. We have S theta functions in the numerator, S in the denominator, and we have this elliptic balancing condition here. I should also mention that the parameters AI and BI, they shouldn't be 0. And we cannot just take limits simply, or contract limits. Okay. And here's some kind of indication why it's really elliptic, because you might wonder what periods we have. But in U, of course, you see the period 2. Yeah. Well, anyway, so I will skip that. Sometimes it's convenient to know in which space we're working in. So I denote E to be the space, actually field of elliptic functions in the variable. It's in U. This would be additive, or Q to the U multiplicative. We have space of total elliptic moderate functions. So if we have several variables with the same periods, yeah. And this notion of total elliptic moderate functions was introduced by Spiridonov more than 20 years ago. Maybe a little bit more exact than years, but I'm not saying which ones are total and which are not. So this is not just. I'm just saying that I'm giving you expressions, and those can be easily checked that they are totally elliptic. Okay. So what is an elliptic hypergeometric series? So this is abstractly just a series whose consecutive quotients of consecutive variables are elliptic functions. We already know that. That means that this quotient ck plus 1 over ck is of this type. And we have elliptic balancing condition. And as we've seen yesterday in Slava Spiridonov's talk, this is the general solution of an elliptic hypergeometric series. We also introduced, one usually requires the series to be finite so that one avoids problems. So that is just about convergency. Of course, it makes sense to look at infinite series, but to study them separately, but that's not theme of my topic today. There's also a notion of a very well-placed elliptic hypergeometric series denoted by V. We will see that 10V9 summation, I have not defined it here, but there's it can be easily defined, but I will just show you explicitly how it looks like. For a little bit of history, okay, the elliptic hypergeometric series appeared, let's say, implicitly as solutions of somehow in work of elliptic solutions of the Yang-Baxter equation and work of theoretical physicists I think already in the 50s and 60s, but then more explicitly it appeared in the work of this Japanese mathematical physicist in 1987, and then 10 years later in the form of explicit identities satisfied by them by Frank Turner. And one of them, and then they were studied also from a pure mathematical point of view without relation to the Yang-Baxter equation or the star-triangle relation by Spiridonov and Cheganov around the turn of the millennium, and also by Ole Warner, who building up a theory of elliptic hypergeometric series in analogy to the basic hypergeometric theory. So here's what I promised to show you. Franklin interlife's 10B9 summation. Okay, it has many parameters. Restricted, there's an elliptic balancing condition here. It's of terminating identity. In the limiting case, so if you don't have p equals to 0, it's just a rational function identity. Yeah, okay. But here we have sums of beta functions. What is maybe important or maybe interesting, if m is 1, you just have two terms, 1 plus a quotient of theta functions equals another quotient of theta functions. And that's equivalent to this three-term addition formula. Okay. And this is indeed, the terms are totally elliptic in several of the variables. But okay. Okay, so now so this is all well known. Now something particular to my methodology. Now I'm using elliptic weights. I'm using these weights. They depend on a position st in the lattice Z2, let's say. And they depend on a and b in addition to the base q and the known p. And we have three theta functions, a product of three theta functions in the numerator and three in the denominator. And of course this is elliptic also, which one can check. And this can be considered an elliptic extension of q. So if you think of cells being computed, if you just count the number of cells, you would have q to the power. But now we have products of these theta functions depending on the locations of the cells, let's say. So this would be a weight of one cell. This would be of a full column. J from 1 to t. Column of height t. So if the t is 0, there is no weight, then okay, the weight would be 1. There's no cell, and the empty product is just 1. So this nicely factorizes, there's a lot of cancellation, cross-term cancellation here in this product. Okay. You see maybe already a little bit of a very well-poised term here, but okay, that's just a small detail for experts among you. Okay, and these are indeed extensions of q and of q to the t. Here's a combinatorial picture, weight of this cell or of that column. And I also need for the commutative algebra, for the quasi-commutative algebra, a shifted version of the weights. So I have this row and I shift A and B both by q to the 2 row. Or if I replace A and B by q to the, if I shift A and B by q to the 2 lambda, then I would have, lambda would be a dynamical parameter and it would shift by 1. So one can interpret it that way. Okay. I also need products of these, which will more or less correspond to big weights of a big rectangle below the path, which if the path is shifted or heightened. And I use Q for that. So big Q means a bunch of Qs, so it's like a bulk product. Many weights I have here. Okay, I just have a compact notation for that. And this is a relation which is used in the for the elliptic commuting variables to normalize them. It's a kind of consistency relation, and it's easily checked for the particular elliptic weights you've seen. So if you look at this elliptic weight here, just these small weights, you have three products in a particular form. You combine three of them here, and you combine them three here. This is more or less a scalar version of the elliptic star triangle relation. That's what I would call it, a simple elliptic star triangle. Maybe you would rather call it a scalar version of the dynamical quantum Yang-Baxter equation. So, as I said, you can see where the dynamical parameters are, but okay. Another form, I haven't seen this product, this scalar version, like everything commutes actually, anywhere in the literature before. I think it will be useful in combinatorial models or integral systems. And of course, where the shifts occur, if you connect these from left to right, you have such a relation. And of course, you can also more sophistically interpret this in terms of this braid relation, taking three strings and Yang-Baxter equation, which I haven't done here. Okay, so here's now the elliptic binomial coefficient, which was known to me from work of 2007 already. So what will be later new will be the multinomial case. So we have these are products of QT shifted factorials, and they extend the classical case. So the Q binomial case in a certain limit, first p goes to 0, then a, and then b goes to 0, and then you would have only these first factors appearing. But now you have additional ones, which make also this whole expression elliptic. Not only that, it's elliptic, totally elliptic in several of the variables, but it also satisfies a very nice extension of the elliptic extension of the Pascal triangle relation. So it's 1 at the border, 0 outside, and here you have these big elliptic weights appearing. And of course, it can be interpreted combinatorially by looking at lattice paths, but I will rather tell you that later if I have time. Well, actually, the lattice path picture is already here. So I want to connect a little bit to lattice paths. So I have a path from U to V with certain indices, KL and NM. I call the family of lattice paths, so I have unit steps going in positive direction. This family is denoted by holographic P from U to V. And I give only weights to the multiplicative weights to the horizontal steps. W and M is the weight of a horizontal edge, which ends in NM. And the vertical steps should have weight 1. So the weight of a path should consist of the products of the weights of the steps. And in this setting, one can also abstractly define a weighted binomial coefficient if one doesn't specify the weights, having a Pascal triangle relation. So if K means the number of steps going to the right, and n minus k those going upwards in total with n steps. So n choose k is like a weighted extension of the binomial coefficient. If we have no steps going to the right, just going upwards, all those weights are 1. If we're out of range, it's 0. And otherwise, we have the last step is either vertical, so there's weight 1, and with a smaller path, or it's horizontal, we have that weight, and we also have a smaller path. And what I discovered in 2007 already, that using these weights, you have a nice closed form product of and you get these elliptic binomial coefficients. And it shifts nicely, so if you start not in 0, 0, but in LK, you shift the path to the right, to the upwards. You have a rule of what happens to the cells using that shift. And you again have a closed form. That's maybe nice also for doing convolutions. So you take the first part of the path and the second part, you have closed form for each part. Here's the extension of the Q commutative algebra, now elliptic commuting algebra. So we have two variables, not just for r equals 2, we will extend that to the general case having r variables, but now we have just 2. we want to normalize that. It generates a simple weight. This simple small weight. Now, the position of the weights, the weights are not the same in the lattice. But so if we move to the right, that corresponds to multiplying this by x, going upwards, multiplying it by y. The action of x means on a and b, on these parameters, means multiply a by q and b by q squared and by y opposite. Yeah? So we have more or less a copy of the same cells, and it's controlled. So if we shift, we know what the new weights will be. Of course, one can just do that, but what really is nice that the binomial theorem works in this setting nicely. And of course, this extends, if there is no a and b, these drop out, these become trivial, and you just have one left. So here's this binomial theorem. So this was known to me a very long time before, but then it got published in 2020 only. So if you, in this elliptic algebra, normalize the coefficients of x plus y to the n, so put the y's to the most right, then x, you normalize the variables, then the x's, and then whatever you have here, a and b should mutually commute. These are these elliptic binomial coefficients. And of course, it's easy to do this by induction using the recursion of the elliptic binomial coefficients. Okay, convolution, I want to maybe just, here is the identity, it's the combinatorial form of the Frankel-Tariff sum. It looks very much like a Q-true fundamental summation, like a convolution of binomial coefficients. Why I say combinatorial form is also because n and m are here integers in this model, but actually if you look at if you rewrite these expressions by their explicit products, you can replace n and m by complex numbers, as long as k is still an integer, a non-negative integer. So this terminates the sum, but you could have alpha and a beta instead, as you have in the classical case, of course. So modulo this analytic conjugation, this is as powerful as the Frankel-Tariff 10b9 summation. So this is like a proof, but the proof is, you have not seen it, but convolution just means x plus y to the n is multiplied by another symbol product and expanded in two different ways. Combinatorially, maybe I just show you here, it means that if you sum from here to here, you get the generating function factorizes nicely, but you can also do convolution along a diagonal. The path has to cross this diagonal somewhere, and the generating function for paths ending in here have a nice closed form, those here have a nice closed form, so you have products everywhere. And the sum, this points can go from L they can vary, that's why you have a sum on one side, okay. Okay, now multinomial coefficients. Okay, now we have not just A and B, we have A1 to AR. We still keep the base Q and the norm P. We want K1 to KR to the integers, whose sum is greater or equal to 0. We introduce some, for notation, the capital letters Ki to denote the sum of the integers up to the ith index. K1 up to Ki, and similar for Ni and Li, which will then appear. And here's now okay, one can define the elliptic multinomial coefficients explicitly as this product now. This turns out to be elliptic, but it also satisfies nice properties. So first of all, okay, I wrote this, instead of n, I wrote K1 to Kr plus Kr right away here. This is the cube binomial coefficient, more or less, with beta functions instead of linear factors. But then we also have these additional factors in this more or less type A product, which you might recognize, especially maybe thinking of McDonald polynomial theory, you have similar products appearing here. Here's this capital Ki, here's a capital Kr, which is more or less the same as this here. Yeah, okay. And for r equals 2, instead of writing k1 and k2, we write just k1, as we similarly do in the classical case. And they happen to satisfy a nice extension of this Q multinomial coefficient recursion. So on the top of the heterodyne we have 1, outside of range we have 0, and otherwise we compute the multinomial coefficient for where the upper index is k1 to kr by the various ways to reduce one of these ki's, the 1. So we have r terms now instead of 2 terms. And this should be now, this is now a big weight already. So there are many factors appearing here. So this is a product for j greater than I. So if I is r, this will be 1, there will be an empty product. And for r equals 1, we will have a big, for I equals 1, we have many factors. So it will increase the number, but okay. And, I'm avoiding the details. So if you actually substitute these expressions by their explicit product representations, factor out common terms, this identity will be equivalent to the Weierstrass type A partial fraction decomposition, which I've shown you before. So it's not a simple inductive extension of the r equals 2 case, but it's a bit more complicated than that. Okay, here's the algebra I'm working in. We have r variables, x1 to xr. We have a field of totally elliptic functions in a1 to ar. And now we want to normalize in this algebra. We have quadratic relations, so actually quasi-quadratic, because the term here does not commute with the others, so we have actually 2 terms here and 3 factors here. So xj, xi, so if it's out of order, we want to order that xi, xj. It generates now a simple elliptic weight with respect to I and j, so we have ai and aj there instead of a and b as before. And now we have this rule, so that if xi acts on a totally elliptic function in a1 to ar, in particular to these weights here, which will appear in many places, it will shift the variables ai by q squared, but the ith variable, the variables aj by q squared, but the ith variable will be shifted only by q. Yeah? Okay. Of course, one can do that, but in addition, it satisfies nice properties. So I call these elliptic commuting variables. And okay, here's just to see that these act nicely on the simple weights. So xi shifts the first index by 1. Application of the action of xy is that the second index t is shifted by 1, and xk, if k is different from I and j, it shifts actually the dynamical parameter by 1, which means here that ai and aj is shifted by q squared each. Okay, one can normalize everything, and the point is uniquely that the result will be unique form. The way to normalize will be not unique. But thanks to the so-called simple elliptic star triangle relation I showed you before, the result is always unique. And here's some indication why this holds. So suppose we have r variables, and we take 3 indices a, b, and c, ordered like this in increasing order, and we want to normalize xc, xb, xa. So we want to put xc to the most right, then xc, then xa, and it will generate some weights. Of course, this can be done in essentially 2 different ways. We can first pair xd and xa, normalize that. It will generate some, and then continue until we finally get xa, xb, xc, and some coefficient before. Or we do that in a different way. We combine xc with xb first, put that in order first, and so we reduce the number of the distance to the normalized form essentially, and that can be done in different ways. And there's actually a consistency relation needed if we want to extract coefficients from normalized forms. So we want that to be equal, and indeed using our elliptic weights, because this is our elliptic star triangle relation, which we already seen, it holds. We have this consistency, and this helps us to work in this algebra. Here's a rule for normalizing a monomial, let's say a generalized monomial x to the k times x to the l. We want to put now the xr's to the most right, and then the xr's minus. So we want to write it in this form: x1 k1 plus l1 up to xr kr plus l1, and this generates many factors, and this is this nice product here. This is the definition I've shown you before of these big elliptic weights and so on. This can be proved by multiple induction, with respect to various L1, L, kr and r and so on. Okay. Now the main result over here, the elliptic multinomial theorem. Of course, no surprise. The reason to set this all up was that this is satisfied. This was the goal. So if you normalize in the elliptic algebra we're working with, this sum x1 up to xr to the power of n, you want to normalize this, you want to expand it in terms of these monomials, then the coefficients are products of theta functions, and these are exactly the elliptic multinomial coefficients I've shown you. It's easy to prove. I mean, here's just a proof by induction. You can just, one factor you isolate, and you apply essentially, you have to normalize a lot of the expressions in between, but in the end, and then you apply in the end the recursion of the multinomial coefficients, so it works nicely. Okay, now we're already at the last part. I want to apply it to obtain something new. The result was not new, but it's at least a new proof of a very nice result, a very fundamental result. In the theory of AR elliptic hypergeometric series, it is the AR Frenkel-Taraif summation, the AR 10v9 summation. And this is now what I would call the combinatorial form of it, which means you have a convolution of multinomial coefficients. And you have a multisum here, and here you have a big product, and everything factorizes completely. It's also important. And the condition, so m, I mean, this is up to, let's say, modulo analytic continuation, just the Frenkel-Taraif summation. M should be still kept a non-negative integer, but the restriction that n1 to nr are non-negative integers can be relaxed, so you can can extend this summation as long as this m is non-negative. Okay, so the proof is simply, I mean, conceptually simple. You just have, it's more just convolution, what I said. You have this big product, x1 up to xr, the sum to the power of n. You split it in two parts, and you apply to each of these terms the multinomial theorem, and then you have to normalize and extract coefficients. And then you get the coefficients themselves, the A1 to AR, they commute with each other. But here in the algebra, a priori, the variables do not commute. So on one side, of course, it's simple. You just extract this coefficient, which is the multinomial coefficient. On the right-hand side, okay, you have to apply this twice. And then you have to normalize. You have to also now move these to the right. And this is done using this lemma, which I said. Where is it? Maybe. No, here it's still not normalized, so I just moved it to right. It shifted the AR1 to AR. Then application of this lemma generates this products of q's, the big q's weights. And then you just extract coefficients and you get this expression where everything commutes. Okay, just here is actually the AR Frenkel-Taraif sum, written in compact form, as Yama has explained in the first day. working multivariables, it's useful to write things as compact as possible. So we write it in this restricted form. So the R equals 2 case is actually the classical case. And this identity was obtained by Jalmar Rosenberg in 2004, but already in 1988, the trigonometric case, the P tends to 0 limit of this identity, was proved by Stephen Milne. Okay, just a few thoughts now. That this actually translates easily to a combinatorial interpretation in terms of elliptically weighted lattice paths in the lattice Z to the R, integer lattice, R-dimensional lattice. And this multinomial coefficient can be just regarded that we take R steps in positive direction along each coordinate. Unit steps. We have n, not R steps, we have R possible steps, but we have n steps in total. So we have n factors, so each step can be either in the first direction, the second, or in the rth direction. So each xi means step in the ith direction, unit step. And of course, we expand this and order it, so and we get all the lattice paths. And we have normalizing gives us weighted lattice paths. So after n steps, we reached some point at the intersection of our lattice with the hyperplane. Said the sum of the indices variables should be n. And we have a precise assignment for the weights with a unit step, the ith unit step ends in the point k1 to kr. We assign it this weight. The product of j's between I plus 1 and r, and these big shifted big weights. So it's quite exact. I mean, it is exact. Yeah. And the nice thing is, if we go to a particular point, let's say we start in 0, 0 and go to the point n1 up to nr, the generating function of the steps with respect to this assignment factorizes completely to the elliptic multinomial coefficient. There's this interpretation. And of course, the refinement is similar. We now fix an integer n less or equal to n and greater than 0. And we distinguish between, we refine according to where, after the m steps, the path crosses this hyperplane, where the sum of the variables is n. And it has to pass that somewhere. And this gives, of course, a combinatorial interpretation of the identity I've shown you before, which turns out to be, and this was actually surprising to me myself, that it is as powerful as the AR Frankel to I sum, because that has many products, but also have many reorderings are necessary that generate many factors. And I think this is the first purely combinatorial proof of the AR Frankel to I sum. Okay, open problem would be there are other Frankel type summations for root systems known. Would this method work, elliptic commuting variables, lattice paths, to give similar proofs for those sums? That's like a natural question. And thank you very much for your attention.
Any questions?
Eric Rins also had a question.
So, what about transformation?
I have not really figured out how to obtain transformations. There's probably something which I'm missing. I mean, there are kind of trivial transformations, but which are more or less sum equals another sum, which is contiguous in a way, but not as deep as the 12v11 transformation, which one would want to prove combinatorially. Yeah.
More questions?
what would happen if you consider non-intersecting lattice paths and use something like SLBNO?
Yes, that I did with with R equals 2 case. That was done, and with your elliptic determinant, which is like a kind of Kartenthaler determinant evaluation. Combined with that, one gets closed form generating functions for families of non-intersecting lattice paths on the plane. But in Z to the R, what do you mean by non-intersecting lattice paths? You don't have this determinantal system anymore. You have lattice paths, they're one-dimensional. You would need more or less hyper manifolds to, I don't know, something like that, which do not intersect. I mean, if you have a path and you have another path, you don't have this property that it can be non-intersecting means you can only arrange it in one way. That fails. So you would need something more general, maybe like, as I said, something like a hyper, what I would now call hypermanifold. You can imagine what I mean. Instead of a path having like a wave in 2 dimensions and then having another one. But that would be maybe, that would add to complexity. Maybe it's related to your AN hypergeometric series, this framework, but I'm not sure. Yeah.
More questions?
Michael, in 2002, I defined an extension of the Bailey chain, and the differential transformation formula was implemented into that directly. In particular, it is exactly the essence of the star-triangle relation, which is defined through this Bailey
Yes,
chain.
but was it the same?
That's what was exactly. I do not see the connection. Maybe you can comment, but
I have a product, a simple product of data functions, but I think you had a sum equals, you had a matrix form.
yes, that's the point.
Yeah.
The role of your weights is played by some particular matrices with the data function identity. So
Yes.
much more understandable thing, because in your case it's some kind of formal operator.
It just, yeah.
So you don't see any direct connection.
I mean, it comes from an operator acting it, but after I take coefficients, everything commutes here. So that's. But no, you had a matrix.
Yes, it's just
form
looking at your relation.
which-
It looks like a product of matrices with particular shifts.
Yes.
And it's similar, but it's not matrices.
Yes, the structure looks similar, but I think it is simpler, and I think it's useful, this relation, and I think it will turn out to be
You
useful.
don't see direct relation.
I don't see a direct
Let's
relation.
say,
No.
I have another comment. So it reminds me that, so in one of my non-commutative geometry papers, I construct a deformation of P1 cross P1 cross P1, or generally P1 to the end.
Okay.
And it's based on a solution of a 2x2 matrix with dynamic Yang-Baxter. And each P1 basically is just a commutative P1, so it's basically generated by 2 things. But then the commutation relations basically say that, okay, there's a 2x2 matrix telling you how to take product of something in the first 2 variables, first pair of variables, and something in the second pair of variables, and swapping the order and expanding those 4
So you think it looks similar to
it looks similar except with a 2x2 matrix version. And I guess that says that for any solution of dynamic Yang-Baxter, maybe there's a similar sort of thing with.
Yes, I agree that because it's still a quadratic algebra what you have,
Yeah.
and you
Well,
just
it's a category, but
Yeah, but whatever.
because of the dynamic aspect.
look, if you look,
Yeah.
you combine 2, it's still quadratic.
Yeah,
So it's not that you have n variables at the same time, but you always 2. Yeah, maybe I should look at that and see if there's a connection. But you have a more complicated rule. You have a as a determinant. So
Well, it's not really determinant. It's just it's the 2x2 matrix
Okay.
expression. I mean, I can tell you offline what the relations are. They're very simple.
okay, but it involves theta functions, or
Yeah, definitely. Yeah, it's an elliptic solution of dynamic Yang-Baxter.
oh, okay, then interesting.
More questions?
I just want to Binomial theorem really implies the so-called quantum pentagon identity. My question is, does elliptic addition binomial theorem implies a certain functional equation for elliptic delivery?
So do you mean the generating function of the...
Sorry?
You mean the generating function of the Q-binomial coefficients? You have the infinite product version? That relation, yeah, that there's some, yeah. I think, yeah, so here it's difficult, first of all, to take generating functions of the elliptic binomial coefficients. Like, I mean, extensions of the Q exponential function. That's what some relation for that, I think. That's what this would be related to. Because of, but yeah, I think that I've tried in that direction, but I have not, I failed to find.
But it's just analog of, elliptic analog of pentagon identity.
Yeah, maybe other people know more if that exists, but Slana, maybe do you know the elliptic analog of the pentagon identity, or is it more complicated?
It's more complicated.
It's more complicated, yeah.
Okay, too many questions.
Okay.
Perhaps some more? If not, let's end the speaker. So I suppose this concludes the conference, and I thank everyone for taking part.
I just forgot to ask one question to Pete. So, today you are birthday.
Yeah, I made a present for myself by giving a talk. Yeah.
Thanks for all speakers and posters represented for presenting us quite a fascinating results, and thanks all participants for coming. We have had a great time together discussing many topics. And I hope all of you developing your subject deeply and make a significant contribution to your research area. Before closing this workshop, I have two announcements. The first one is on proceedings. We will publish proceedings from advanced studies in pure mathematics. Publisher is the MSJ. And yeah, surely all invited speakers and poster sessions representatives that are invited. And I hope some other participants can contribute. And the second one is on the next workshop on elliptic integral system. We have decided with international advisor Eric Reins, Slava Spiridonov, and all Varna and Edwin Langman. The next workshop will be held in the US. Probably, hopefully, Simon Center for Geometry and Physics, organized by Eric Reins.
In 4 years? In 4 years? 4 years?
Do you speak?
Okay, if I'm organizing it, never.
Do you speak something? Oh, next one. Your hope.
It's too early.
Too early?
No,
It's too early.
there have been thoughts
It's
about
just
where to apply
preliminary
to have
discussion,
it,
so it's
and
too
we'll see
early.
what happens.
Okay.
It's years.
Okay. In any case, yes. See you again in the US. Thank you very much.
If it's Simon's, it's easier.
Easier.
Yeah, I'll organize for like.
So,
Yeah, I mean, like, you know, the proposal is quite reasonable.
probably.
Yeah, my Yes, we're going to represent the workshop was it was very you all hard work.
Yeah, actually, we need someone who can wrote a physical proposal. And yeah,
Follow up over the email.
we are considering.
But like when? It's like not in 4 years. 2 years? Because if we organized something there last year, maybe like 2 years, like 25. Like summer 25. So I think we have reviewed twice of proposals to just apply, like, you know. Yeah, it's really like, you know, organize this program, but like work was minimal. Like we submitted like 1 page of proposals, and it was accepted. We got some like $100,000 like quite yeah. Well, that's not it yet, but that's how it was not like